Now, it is the application of Gauss-Bonnet theorem. Suppose ABC is a geodesic triangle that is given. It is a geodesic triangle consisting geodesic arcs AB, BC, and CA, and enclosing a simply connected region R. Right? So, suppose this is A, this is point A, this is point B, this is point C. So this curve AB, BC, and CA. This is a exterior angle pi minus A with a tangent between these two curves, and this is pi minus B, and this is a pi minus C. Right? Now angle between the tangent to the arc at the vertices at A, B, C are pi minus A, pi minus B, and pi minus C because these are the triangles. Now geodesic curvature, which is equal to 0 for geodesic, then it means kappa g is equal to 0. If kappa g 0, then this integration is equal to 0. If this integration is 0, then exterior of C dash, that can be written as 2 pi minus sum of exterior angle. So what is sum of exterior angle? Pi minus A plus pi minus B plus pi minus C. So this is A plus B plus C minus pi, this values, right? So this is a exterior of exterior. So this is a EX of C dash. Now from this total curvature of geodesic triangle is equal to 0. So it implies the total curvature. We know that this is a total curvature of the triangle. So total curvature of the geodesic is equal to 0. So that is a first just example of Gauss-Bonnet theorem. And similarly, what is Gaussian curvature? So that is definition. Let P be any given point, and this is the area of a geodesic triangle ABC. ABC is a geodesic triangle, and this is the area, and P is a point in this inside this triangle. At point P, we have limit A, B, C approaches to P. This approaches to P, B approaches to P, C approaches to P. And this limit of A plus B plus C minus pi over this area of a triangle. So this is called K, geodesic curvature, right? Gaussian curvature. So this is a Gaussian curvature. The formula of Gaussian curvature is A plus B plus C minus pi over area of triangle when A, B, C approaches to P. Clear? So this is a definition. Now find the Gaussian curvature at any point of sphere. Now we know that on sphere of radius A, the geodesic are the great circle, and area of geodesic is given by A square A plus B plus C minus P. Then what is Gaussian curvature? So that using the formula A plus B plus C minus pi over area, this area, that total value is 1 by A square. So just used that formula. Similarly, to find the total curvature of sphere, so total curvature is equal to K into ds. We know the value of K, so substitute, then we get the value of total curvature. So in this way, we can find by using that result Gaussian curvature as well as total curvature. So here we can find two values. One is Gaussian curvature, second is geodesic total curvature. Now next article, geodesic mapping. So almost it is the last article of this chapter. So geodesic mapping. A surface S is said to be geodesic mapping A surface S is said to be geodesic mapping onto a surface S dash. If there exists a differential homeomorphism of a surface onto a surface S dash, such that the geodesic on S go over into geodesic on S dash, right? So that is, now we have, this is some surface S, this is some surface S, and this is some surface S dash, this is some surface S dash. Here. Now, if there exists a some differential homeomorphism from S to S dash, right? There is some homeomorphism. If this is a some homeomorphism from this to this, clear, this surface to this, and this, it's, if it is a geodesic, it is a some curve which is a geodesic in surface S, we take its image that is again geodesic in S dash, then this mapping is called a geodesic mapping. Simple. That convert the image of geodesic is geodesic. Go over into geodesic on S dash, right? So that is go over. Clear? So that is go over the geodesic of the, go over such that the geodesic on S go over into geodesic on S dash. Clear? So it contains geodesic as we. Now this is very important result, state and proof, Tensor theorem, and we can. So in this theorem, the statement is if S and S dash be two surfaces, then in any non-conformal homeomorphism, regular at each point, regular means analytic, right? At each point, mapping of S onto S dash, then there exists at every point of V of surface, there exists at every point of P of surface S a uniquely determined a pair of real orthogonal directions such that corresponding direction on S are orthogonal. Clear? So we understand the statement by proving the result. So we take basically two direction in S, and our aim is that these two directions are perpendicular in S dash. Clear? So we have two surfaces. One is S and second is S dash. So in S we take two directions, L1 M1, L2 M2, and their corresponding direction in S dash. These are L1 M dash, M1 M dash, L2 dash, M2 dash. These are corresponding direction at Q of S dash. Our purpose is these are perpendicular, these are orthogonal, and our purpose is these are also orthogonal. Clear? Now let L1 M1 and L2 M2 be orthogonal direction at point P of S. And similarly, L1 dash M1 dash and L2 dash M2 dash be corresponding direction at Q of S dash. And what is our aim? Our aim is to show these directions are orthogonal. If we want to prove that these directions are orthogonal, then we want to show that E dash L1 dash L2 dash F dash the property of orthogonal. Clear? Now EFG related to S and dash is related to S dash. So remember. Now because these directions are orthogonal, then it satisfies this property because cos of angle is 0. Then this is a value of cos of angle. So this is equal to 0 by equation number 2. So this is in equation number 2. We know that this L1 dash, which is equal to L1 ds by ds dash. So that is arc length in capital S that is arc length in S dash. These are direction in S, these are direction in S dash. Clear? So by using this result, this equation number 1, that is given. This can be L1 dash and L2 dash written in the form of L1 and L2. Clear? When we used this result in this equation, then this will be common part, ds by ds dash. So this will be common part. If this will be common part, equation 1 can be expressed in this form, equation number 3. So simply used these values. It means L1 dash equal to this, L2 dash equal to here change L2, remaining is same. M1 is here change M1 and remaining is same. So substitute and we get this values. Now from equation number 2, this is equation that our purpose that that we want to prove. The equation number 1 we want to prove that, and that is a given. Equation number 2 and 3. If 3 will be satisfied, right, and that 2 is given, from equation number 2 we can find L1, L2, right? So we from equation number 2 eliminate L1 and M1 from that equation. So one part L1, M1 eliminate. So when we eliminate this, we get this kind of differential equation. So it is an equation of order 2 quadratic equation. So this is quadratic equation, not differential equation. So it is a quadratic equation is L2, M2 and this values, right? Which determines two orthogonal direction at each point. Why? Because it is a quadratic equation, it has two directions. Now, it's what is the condition of orthogonality? When we already discussed, the condition of orthogonality is ER minus 2FQ plus GP equal to 0. Now here, what is P? This is P. This is P. This is Q. And this is R. Right? P, this square plus Q plus R. So what is P? P is equal to, by comparing this is Q, this is R. So this is R. Now substitute here. If we substitute here, this is R, P, and this total value will be 0. Then it satisfies the condition of orthogonality, right? It satisfies the condition of orthogonality. Now, in addition to that, in this quadratic equation, discriminant is positive. We can easily check that. This is because of this E is a non-zero. If discriminant is positive, capital E is because non-zero, then mapping is a non-conformal. That we read in the complex analysis, conformal mapping and non-conformal. So since a discriminant is greater than 0, roots are real, roots are distinct and real. We know that roots are real and distinct, so which confirm it is uniqueness. So also it confirm the uniqueness. So in this way, we can prove this result. So this is a desert theorem. So this is very important. This is the end of this geodesic section, the geodesic chapters. So this was the last theorem which prove also its uniqueness. So in this case, these are two surfaces. In this surfaces, if we have two direction which are orthogonal, so their corresponding direction are also orthogonal. So this is the end of the geodesic. So thank you very much.